Hello, Luke.
Hello.
Is that loud for you?
Oh, you've got.
Yep. Oh, you guys.
Or the wall speaker?
It is the wall speaker now, right?
Yeah,
Yeah. No, I was asking, is it too loud?
it's not too loud.
Yeah.
I noticed a difference this morning when you were doing.
Oh, you can hear it. Okay, then we should get it down. Yeah. I think in the morning I didn't bother because I was the only one. I didn't care for. Then I should be careful if because you're right next door, right?
I think so.
Like we have a wall. Okay, so let me see. Can I speak again? One of you guys? Hey, Jordan.
Hello.
Hey,
Can go down a little, right? Again, I'm just working on the volume here.
yeah, I was looking.
Okay. Can you hear us?
Sounds good. Yeah.
I was looking through the classical mechanics class just to see
What's going on?
Because I have to register
Eventually.
a qualifier.
Okay.
I was looking through and I thought, wow, the first three homeworks I recognize, 80% of that.
Yeah, I mean, it's kind of building up, sort of the Lagrangian part and all that. So,
Can you start with functional derivatives again?
I started the third week. Is that better? Yeah, I started the same thing, but on the last year, the first week was functional derivative.
Yeah.
And now I gave it a little room, so I thought first I will go through some simple Newtonian physics, and then in the third week slowly put it in.
Gotcha.
So now that you guys are finished, how was functional derivative? Was it rough?
It was useful to learn.
Okay.
I liked it.
Yes.
I thought it was good.
It was good. Okay, good. Glad to know. Yeah.
Because I never really.
Go ahead.
I just had never been presented it in that form before, so it was nice because it applies well to classical mechanics and a lot of problems that you solve. Makes it simpler once you know how to do it for sure.
Yeah, exactly. So it's to my knowledge, I mean, even though many people know it, it's textbooks never deal with it in that particular sense, and I feel it is probably they don't do it because of the functional derivative concept. It's a little harder probably to digest, but once you accept it, it becomes very systematic to do the Lagrangian. So
yeah, that's a good way to put it. I also bought the textbook that you mentioned. I can't remember the name of it.
Gelfand and Melvin, I think.
It was a small textbook.
Yeah, it's a Russian textbook.
Yeah. No.
Gelfand, yeah. Okay.
You had the qualifiers. Did you are you planning on taking the qualifiers this time around?
Yeah. I did the free one last time.
Mm-hmm.
So this time this is the time that it's like, I have a mission to get through.
Yeah, for sure. I was just wondering if you knew when it was.
They're probably going to be.
That was this.
Yes, Gelfand and what's the second name for Fomin? Yeah, Fomin. Yeah, very nice. But I take only first chapter or two chapters. I think I used in the class mechanics. Yeah.
And my wife is so thrilled that me going back to graduate school, my purchases of different textbooks has gone on the increase.
Mm-hmm.
I'm going to need another shelf.
But yeah, textbooks. I think one should. At least whatever you go through, I think one should. At a graduate level, it's good to have one of the classics as an excuse for the textbook. Even though I don't use textbook so strictly, but I always recommend that buy the textbook so that it's good to have it material that
That's
they
how I
can
do
refer.
undergraduate classes. The textbook is loosely our direction.
But yeah, I also understand the importance of a textbook, so yeah, I struggle there. That's my big issue. Yeah. Okay. Anything else? So who are we missing? Alia. 1, 2, 3, 4, 5. Yeah. Alia. Okay. Should be here, I suppose. So Jordan, how was the basement cleaning? Did you? Was it
It was
loud?
amazing.
Was it
Loved it.
loud? Was it loud out there? Is that why you didn't want to put on the audio or?
Yeah. So the story goes like this: the people that rent the house didn't turn their heat up high enough. I guess they were trying to save money, so they were just like using blankets and stuff, and so their pipes froze and burst. As the ice expanded in the pipe, it caused the pipe to bust, and then their basement filled up with like 2 inches all the way across the bottom. It's like a concrete basement, just full of water. So I had to use a sump pump, and the sump pump was running while I had a headset in. But, if I turn it on, then all you'll hear is like a loud screeching pump going. So I had,
You were
decided not to
working
have
while you were
audio.
listening to a graduate level physics course, huh? Happens only
Yeah,
during
I
the
had a headset in while I was watching the pump, and I was just looking at my phone. It's fun.
Very soon
It
we'll
worked.
hear stories about people going in the subway in the cities and they're attending courses there.
Yeah.
The subways, there is you're bored usually there, right? Everyone is sitting there and I hear people start attending courses during that time.
We're getting close to Star Trek in that respect. Remember that they would have a little pad they would be doing classes on during Next Generation.
Yeah. Well, I don't know where we are heading to.
But it was nice because I just listened. I didn't actually write anything down, and I went back and watched the lecture. And I didn't realize the benefit of not actually taking notes and just paying attention to what you're doing, and then going back and really taking notes. That's the first time I've ever actually just listened to a lecture and then went back and watched it and took notes. So it was good. I felt like I got a lot out of the last lecture.
Yeah. Let's see how all this evolves. Okay, so okay, you guys keep chatting for a minute. I need to set this.
See, Jordan would have been okay if you'd have kept the cameras on the back of the room and did the lecture. He just listened. I agree, though. It does help sometimes to hear it.
Well, you don't realize the little bits and pieces that you're missing when you're multitasking, of like writing while someone's speaking.
Yeah. I'm a horrible multitasker, but then Alia is there. Alia to take care of her kids. Once you have kids, you don't have a choice, I guess. So you cannot complain there. So we still have the choice to complain. Okay, I think it's good. Nice. Okay. We have homework. No, that's not correct. Right? Homework 3 is going on.
Yes.
Homework 3 is going on February 9, I suppose. I don't have it entered here. 2, 1. 2 weeks from Tuesday is the exam. Oh, how should we have the exam? Any suggestions? Shall I make it during the class session itself for 1 hour 15 minutes, or do you guys want to take home?
It doesn't matter to
From
me.
a learning perspective, I like take home, but I think the in class is fine as well.
Okay, so I have
I think the take homes, I think, if they're written as a take home, take a lot more work, but you have a lot more,
time
we also have a lot more that you get out of it.
you get out of. So that's Jordan say, you learn more with that. Correct? Okay.
I think
Any other-
from like a beneficial standpoint, I think you definitely learn. You retain maybe more of the information that you worked on that exam in the future. I guess you could do the same with it in class, but you'd have to spend more time after you took the exam reviewing it, and
Or
there's usually stuff going on.
prepare more for the exam, but probably it's easier to just assume that, oh, I know everything and not work for the exam, or you're busy with everything.
I think I prepared the same for both the take home and in class. I think I really wanted to know what I was doing come exam time instead of just learning everything when I got the exam.
Okay.
The other thing with the take home is if you bought something up, you've got the time to circle back around and try it again. Except when you're in class timed, it's pretty much it's mistakes and all.
So what's the difference between homework and mid take home?
I think just time. I think when you have homework and midterms, then you have an extra tack on. So when you did the take home the last time, we didn't like postpone the homework or anything. So you actually still had homework and a take home exam. So I guess you could say it's like 2 homeworks, but
You're saying homework is usually having 1 week to work on, midterm is only 1 day to work on. That's the point?
I think, well, the way you did it last semester is the take home. I think you had a few days to complete it. If you assigned it like on a Thursday, you gave us to like that Tuesday to complete it, if I recall. But
Okay, maybe I can phrase it in different ways. One of my complaints with the homework is, as far as assessment goes, is that often you go to the resources and sometimes it's not all of you guys. Sometimes I see things being presented in it's clear that it's not, and you guys didn't understand it, or some of you guys didn't understand it. I'm not saying all the time, every time. Sometimes you know that, oh, this is not okay, like not acceptable sort of. And I cannot take off points because 2 steps will be wrong, but the 3rd step will get fixed automatically because you know where to reach eventually. So, and it's harder to take off points there. So my point is, how can I avoid that? Maybe I'm asking you guys, how can I avoid
with the take home or
Yeah.
the homework?
Or with the midterm, or either way actually, because do you guys see what I'm trying to say?
I think if I were to do the class, the way that I would do it is the way that you grade the take home midterm should be tougher than the way that you maybe grade homework or an in-class exam. So if I gave you the same exact, if you give someone a 90% on an in-class exam on the same problem, you might be able to take off more because, on a take-home exam, because you've allotted them the time to complete it. So, yeah.
I think
so. I think, yeah.
Okay, is that acceptable? Like, is that fair enough? Do you guys think that midterm will be graded heavily? Right?
Well, the question, when you were saying that you'd have like 2 steps that weren't really right, and then the next step, because either they knew where they were going with it or whatever. I think making the work support the result
It's necessary.
is very necessary.
I know. At the same time, I feel, how do you say that? I mean, sometimes it is very obvious that what is going on is correct, but I have to also defend my grading, right? So I try to be very defensive in the sense that I don't want to take off a wrong point. Sometimes there is a implicit connection. You say, oh, yeah, I meant that, but I didn't write it. And I give a lot of room for that in graduate level. Like undergraduate, I'm very strict about, oh, no, it has to be there, it has to be correct. But here you can be okay. Sometimes people imagine things and you can get the correct answer. So I do give that room, but sometimes I do want to be strict. And the first homework was a classic example, like for this course, the first homework. I was not happy with many of you guys. Like, let's say I don't want to take names, but half of you guys, because you knew where to go, where to reach. So, but there were some intricate steps which many of you were missing, and I was not very happy. And maybe I was hesitant to take away points also because it was the first homework. Sometimes nice. So grading. Okay, how about that? So I'll take that. I'll grade hard midterm. Okay, so expect that. Okay. So that's reasonable, and then it will be take home. Okay, we'll have a take home, just a little harder grading. Maybe homework also, if you allow me to little grading.
I think it's better for us if you
I think you just grade us on where you feel like our level of understanding is on the problem. Even if the answer is right, I'm okay with you saying like, well, maybe I don't see you taking all the steps and procedures here. So just say like minus 10 points because yeah, you got the right answer, but I don't really see the logic from step 1 to step 2 maybe.
That gets hard very quickly. I have noticed that if I really grade correctly and there might be failures. So if you really want to grade at the level of the world, like electromagnetic course in the world, then it gets hard actually. Even if it's not world, let's say last 5 years of teaching in SIU, sometimes you get a huge variation. One might be exceptionally good and there might be a person who is trying hard. The worst is when students are trying hard and they're not getting. It's easier to fail them when they're not working. I don't mind at all that. But when they're really trying hard and not getting it, so I feel a little odd about it. So I try to help. At least I get confused there. So I tried, earlier I used to grade it in such a way that anyone above 60 to 70 is B minus, 70 to 80 is B, and so on. But these days, I think I got too lenient. Last semester was an exception that was different because of the COVID and all that. Usually as in-class exam is where people really lose points. Like the moment you take that off, suddenly everything gets boosted up for some reason, which is understandable. But anyway, so I'll bring this up again. We have 2 more weeks to go. Yeah, but take home by, unless I really get mad at something that I see in your homework or something, I think take home is okay. I'm okay with it. I do feel that take home is a good way of learning. I agree. Yeah. Okay, so I think let's a few minutes of talking takes away. Okay, I think we should do. We said we will talk about circular wire, but more importantly, magnetic dipole moment. So let's say circular wire, but circular wire, right? Circular current carrying wire, but more importantly, this magnetic dipole moment. In what sense is it magnetic dipole moment, you're going to say that the radius of the wire is really small. So this is the real magnet. Whatever you're going to talk about is the real bar magnet that you think of every day. This is exactly a bar magnet. So let's have a loop of wire, current carrying wire, that's say I out there. It has a radius A, so that's your axis. Let's say it is along the z-axis, aligned with the z-axis. That is a radius A, here A. And there is an observation point, right? That's an observation point R. And we would like it to be anywhere around. That is even though the loop has a plane associated with it, so it's that this kind of shape, but it's actually a ring. You can always think of a sphere, right? So, spherical region around that. So you don't want to be in that region. You want to be outside that region, and that's what the approximation is going to be. So we're going to work in far field approximation. So far field, I think far field has a hyphen in between, not very sure. Far field approximation. Is basically there is R, which is, or A is extremely small compared to the observation point R. The distances at which you're measuring the magnetic field is very far compared to the size of the loop, in the sense that you can actually take the limit A tends to 0. Once this is true, if you're within 2 significant digits or something, you can set A equal to 0. So within our approximation, you can set A equal
Just
to
the same kind of concept with optics, like far field, near field stuff.
What do you mean by optics? Tell me a little more. Yes, probably yes, but I can make it a little better.
Like in a slit experiment, depending on.
That's correct. That's correct. That's correct. Yes. In fact, we will do that later down in the semester. I don't know whether we do the slit or not. In general, radiation problems. Like currently, notice how we are working. We are working electrostatics separately. Now we are doing magnetostatics separately. And each of them are complicated enough. We already see that exact solutions are very rare. You put them all together, it's almost impossible to get exact solution. So in that case, only in these kind of approximation, very extreme approximations, you can get anything going. But these approximations are so good that it's okay. It's like if you're seeing an atom and you say that your observation point should be 10 times more than the radius of the atom, of course, we are always 10 times more than, a million times more than. So in that sense, it always is a very good approximation, but nevertheless, it is an approximation. So you should go beyond. Yes, so yeah, optically, yes, that is, it is, we will keep using this later on also. The context will change. Okay, so J again was current density, so that's an approximation overall point. So J, magnetic, no, what is it? The current density, right? Current density. Our prime is equal to, we said, what was it? Current is phi hat, right? So phi prime hat, and that's a direction. That's a current I. So yeah, current I and help. What else is that? Rho prime of A, so that's one distance. I need an area in the denominator, and there is a Z prime, right? Z prime. I think that's what it's. So that's current per unit area, and as a direction in the tangential to the loop. Our vector potential is mu naught over 4 pi d cube r prime, r prime over r minus r prime. And yes, so we would like to, so let's plug that in. So this is A of r prime for this particular situation is mu naught over 4 pi dz prime, or what should I leave? Yeah, dz prime minus infinity to plus infinity, 0 to infinity rho prime d rho prime, and 0 to 2 pi in cylindrical coordinates. And here phi prime vector, phi prime. And let me bring out the I outside. Is delta of rho prime minus A delta z prime, whole thing divided by, still in the lower region. Okay, this is the magnitude of point R vector, the observation point R, but the source point is somewhere on the ring. Right? That's where it hits. But for now, we don't have to assume that R prime could be anywhere. These delta functions are what is going to pick that out. In general, we have z minus z prime square plus the vectorial, the cylindrical coordinates vector, two vectors in a plane, subtract that out. So there was a small confusion there earlier in discussion. So let me write that quickly. Do that. So vector R is equal to, in cylindrical coordinates, z in the k direction plus rho, right? Where vector rho itself is equal to rho cosine phi I direction plus rho sine phi j direction. Correct? That's your cylindrical coordinate. So r minus r prime would be z minus z prime in the k direction plus rho cosine phi minus rho prime cosine phi prime in the I direction plus rho sine phi minus rho prime sine phi prime in the j direction. Correct? How to square this? So magnitude of r minus r prime squared is equal to all three quantities together. So that's z minus z prime squared plus, there's a square from here, cosine square, sine square, that's actually 1, so that's a rho square. Correct? There's a squared quantity coming from here, sine square plus cosine square is 1, so that's a rho square. Similarly, the next term, there is a rho prime square. It's not negative, so it gets squared, right? So it's not negative. But the next term, there's a cross term, which comes with a negative sign, rho prime, and that is cosine of phi prime, and then plus sine of phi prime, which is using trigonometry relation cosine of phi minus phi prime. Right? Cosine angle, what is that called? Two angle formula, I think, is phi minus phi prime. So that's your quantity here. So let's put that there. So that's rho square plus rho prime square minus 2 rho prime cosine of phi minus phi prime. Okay, so it's good to at least have a feel for where that came from. Okay. Okay. Any questions, remember? Can you guys ask? That's one line. Okay. So we can, let me do the, since there are delta functions, immediate integrals, let me do the rho prime and z prime integral. So z prime gets set to 0 and rho prime gets set to a, right? And the a comes out, there's a rho prime here that comes out there. So that's mu naught over 4 pi times I times a. And there is an angular integral that remains 0 to 2 pi. It's d phi prime. And the numerator, it is phi prime. So that's all that stays up in the numerator. So that's phi prime. Think so? Yeah. And the denominator, it is z prime gets set to 0. So that's z squared plus rho squared. And rho prime is all a, right? Plus a squared minus 2 rho a cosine of phi minus phi prime. And the whole thing inside of the square root. Okay, the only distances that is showing up is in here. What is z square plus rho square? What is z is this point here. That's here z. Oh, my diagram, I'm drawing in the wrong region. Yeah, so that's your z, correct? And this is your rho. So rho, z, and there is an a, right? That's your 3 quantities that's showing up. So z squared plus rho squared has to be r squared. So that's r. So surely this is r. Okay, and remember our far field approximation says a small compared to r, right? So that's our condition. There, so this is R. So let me, since we are working in R is not dependent on our phi prime integral. So let me pull that R outside. It's equal to mu naught over 4 pi I a over, when I pull this R square out, it becomes an R, right? Because it's a square root there. And there is phi prime hat. Let's leave it as it is for now. And R is taken out, so what is left is 1 plus a square. So let me do that in minus. First, let me write minus, right? Yeah, 1 minus 2 times rho over R and a over R. And that is cosine of phi minus phi prime. And that is one more term, that's a squared over R squared. Okay. I can do this at this stage or at a later stage, either way. Notice that in our condition that R is very much larger than A, and rho, remember, is part of R itself. Right? If R increases, then rho also. Actually, not necessarily, right? This need not be always large. I can have this to be of the order of 1. Like if I'm on the z-axis, for example, right? rho, if I'm on the z-axis, that is actually 0. But if it is exactly on a cone of 45 degrees, then r is equal to rho. So this can be 1, or in fact even larger than 1. So this need not be always small, but this is always smaller than this. This always is smaller than this, and in that sense, we can neglect that. So in the far field approximation, the contribution from here will never be more important than the contribution from here. So this will be the leading contribution. This will always be the next to leading contribution. I can do that after I invert this, or I can do this at this stage. It doesn't matter. So I will drop this term. So in that far field approximation, it is okay to drop that term. It will have a contribution, but it will always be a second order contribution.
Can you drop the camera now?
Oh,
Just a little bit.
Sorry. Yeah. So again, I think you guys missed whatever I was saying.
Yeah,
Yeah.
no, it's okay. I think we got it.
Yeah. So I'm dropping this term compared to that. Okay. Remember that there is either way. This is still small, right? If this small, so there is 1 over 1 minus x is approximately square root of it, right? Is approximately equal to 1 minus 1 by, no, not minus, 1 plus 1 by 2x, right? The minus sign from here and minus sign from the power, so it is 1 plus 1 by 2x, and there are higher order terms, plus order x squared. So if I use that, that's equal to E naught over 4 pi I A over R, and I have 0 to 2 pi d phi prime. There's a phi prime hat, that's a vector, angular dependence inside in there. And now I expand this out, and this is 1 plus 1 by 2 of whatever that quantity is. So that's 2 times rho over r, a over r, and cosine of phi minus phi prime. The first term here, the 1, multiplies this integral. So 1 multiplies this integral, and what is that integral equal to when it multiplies at 1?
0.
0, right? Because this is an integral of a tangential unit vector, and we used this in the last class also. That's 0. So this term doesn't contribute actually, which is the point that if the leading order is coming from here, so otherwise it is actually not that at all. So 0. If it was not 0, then we didn't even have to go here, right? And this becomes our leading order. That's a over r. Like there is a over r right in the front, so that's our leading term if you want. But if you keep this, then you get 0. So you want some non-zero value, leading term, not the first term. So the leading contribution is coming from here. But now rho a and r are all phi independent, so that can actually be taken out of the integral. So I can do one more step. So it's mu naught over 4 pi, and 2 cancels out. There is an IA square, right? That's, remember, your magnetic moment is area times I, so that's a nice combination to have. So this is IA square, and then there is rho over r cube. And dimension of vector potential is just the current times mu naught itself. So this is all canceling out. And that is angular dependence in there. So let's see what is angular dependence. So now we have to do this integral. phi prime hat times cosine of phi minus phi prime. If this also goes to 0, then we have to go to the next order. Right? Then we have to go to the a square term. Let's see if this has any contribution. Okay. Again, the hope is that we can get some magnetic or since I wrote the topic as magnetic dipole moment, so this will the circular wire will be interpreted as a magnetic dipole moment, and the expression will come out in terms of magnetic dipole. What is an integral equal to? Let's go and try to do that, and then we have the expression, right? Almost immediate after that. Any questions at this stage? Okay. So what is that integral? So this is 0 to 2 pi d phi prime vector phi prime and cosine of phi minus phi prime. Expand it out, right? So we have to integrate over phi minus phi prime. Various ways of doing it probably. Easiest way, I don't know. The blunt way is to just expand it out. But there might be some geometric way where you take the component of this cosine as a component. Right? Maybe there are some neater ways, elegant ways there. But let me do it the blunt way. So I'll do 0 to 2 pi d phi prime. Phi prime, remember, is phi prime. This is your rho prime. And that's angle phi prime, and phi prime vector is perpendicular to rho prime. In that sense, this will have minus sine phi prime in the I direction plus cosine of phi prime in the j direction times cosine of phi minus phi prime. So we have two integrals. I hat doesn't depend on the angle. 0 to 2 pi d phi prime minus sine of phi prime cosine of phi minus phi prime, and plus j hat 0 to 2 pi d phi prime cosine of phi prime and cosine of phi minus phi prime. Expand it out again, the cosine expansion minus I hat 0 to 2 pi d phi prime. Cosine phi is what? Maybe I'll jump a step. I'm going to do this. So there's cosine phi prime, but cosine phi is independent of phi prime, so I can bring that out. Hopefully this doesn't confuse too much. Sine phi prime, cosine phi prime. So that's the first expansion, cosine phi prime. The next one is still positive. So which is having there's a negative sign in front, so it's negative I hat. Sine phi comes in the front, and 0 to 2 pi d phi prime sine phi prime sine phi prime. Is that clear? I just did the first integral, broke it into two. Hopefully it's not too off. Hard to interpret. Again, the same idea, cosine phi here. And this is d phi prime, 0 to 2 pi cosine phi prime, cosine phi prime, and plus j hat sine phi times 0 to 2 pi d phi prime, cosine phi prime, sine phi prime. Okay. a product of two or sine and a cosine is nothing but sine of two angles, right? 2 times phi prime over 2. So maybe let's do one more step by now. Since we have so that's minus I hat cosine phi. I multiply and divide by 2 there, so that's 1 by 2, 0 to 2 pi d phi prime, and this is sine of 2 phi prime. Right, because sine of 2 phi prime is 2 times sine s cosine d, right? And this is sine square term minus I hat sine square theta is how much? Sine of so this is 0 to 2 pi d phi prime, and this is 1 minus cosine sine square phi, so it is sine of 2 phi prime over 2. Correct me if I'm doing all this by any mistake. Yep. Plus j hat cosine of phi 1 by 2 0 2 pi and 1 by 2 needed that d phi prime, and this is 1 plus cosine 2 phi prime over 2, and finally plus j hat. I'm sure there is a nice simple way of doing this in a geometric way. This is d phi prime finally. This is 1 by 2, right? D phi prime sine of 2 phi prime over 2. But sometimes blunt ways are also okay. Okay, any questions there as of yet? That's just blindly doing the expansion. What's the integral of 0 to 2 pi sine of 2 phi? It's 0 to 2 pi. Zero, right? Because it is a periodic function. Even though it is sine 2 phi, it actually squeezes down, right? So you're actually going 2 periods. So it's 0. So since it's a periodic function, that goes away. This goes away, right? What about cosine 2 phi? Same thing. It's double. You're going into 2 periods. You're actually squeezing the cosine function. Right? Cosine function is like this. That's 1 period. 2 phi is actually going from here to there. So that's 2 times that. So this cancels out. The areas cancel out. So this cosine 2 phi also cancels. The 1 doesn't cancel though. 1 can contribute, but this is periodic. So that goes away. This goes away. And that's it, right? Most of it went away. And what is left out is there's only this term here, right? So as a 1 by 2 times 2 pi, when you integrate, you get a 2 pi, so it's pi. So it's a minus I hat times pi times sine of phi. Because this integral here will give you a 2 pi divided by 2. That's a factor of pi there. And plus j hat times pi times cosine of phi. And what is that? It should be something familiar. We already used something like this. So if I were to take a pi out, so forget the pi here. What is the quantity in the square brackets?
Phi hat.
Yes, that's phi hat, right? Very good. So that's phi hat itself. So you integrate over phi prime hat. Notice one was an observation point, like observation. So there was a loop here, and there were phi prime hats there, and the observation point also has a phi hat going in there, but they don't have to be in the same direction, right? Because you could be having it. This could be anywhere, but when you integrate over all of them, add them all together, in fact, the answer is in the direction of phi hat. So the vector potential will be in the direction of phi hat. That's what it's saying. So if we use this out there and pi, notice that we were missing the area required of pi. So that gives you that factor of pi. So that's nice. Remember, we want that moment of magnetic moment. So it seems like it's all preparing for identifying the magnetic moment. So this is mu naught over 4 pi times, this integral is done now, so it's pi. So it's an I times pi times a square, current times area, that's magnetic moment, and there is a rho, extra rho there, divided by r cube, and all in the direction of phi hat. Very simple answer. That's magnetic vector potential. Notice magnetic field we know is, so think of a bar magnet. A circular wire is nothing but a bar magnet. Like magnetic field is like this, right? Or a bar magnet. Right? But now we're talking about vector potential. The curl of this is what is going to give you that, right? So curl, this is in circular. Right, so somewhere here, so these are all circular, and curl of that is going to give you that simple expression. Notice very compact, simple. In fact, we're going to make it simpler, right? Because that's magnetic moment, M. Right? So this is M times rho. In fact, we will make this better. So let's actually go to the next code. So field A at observation point R is mu naught over 4 pi. That's because of the dimensional reasons. Units gives you that. And there is M times rho in the phi hat direction. So that's a combination. And there is R cube. And M here is I times pi and the square. Current times area is magnetic moment. But it would be nice if we can write this in terms of the direction also. Magnetic moment has a direction, correct? So it seems like it is only the magnitude that is coming up, right? So let's do better. So let's go back and let's see. So this was our loop, right? And that's our z hat direction. Or let's say that's our M, direction of M, right? Like M is perpendicular to the loop. And, oh, there's no prime, right? That's phi hat. Phi is, of course, it depends on the observation point somewhere here, and that's your R. In fact, forget the loop, right? Once we have the magnetic moment, that's all we need. The information about the radius is gone, right? That's inside the magnetic moment. And that's your vector R, or hat or R. And where is phi hat? Phi hat is, if this is these two are in the plane, phi hat is going into the page, right? So that's phi hat. Correct. And now let's, I want to capture that, this numerator in terms of this vectors M and position vector R. So let's see, what is M crossed with R? What will be the direction of M crossed with R? Oh, what happened to the sign? Did I miss a sign somewhere?
Just out of the board.
Yeah, out of the board, that's correct. Okay. I think I'm missing a sign. Okay. This is M cross is out of the board, right? Okay, out of the board. So it seems like this is out of the board will be minus, since I have to be at every point, so this is minus phi hat. Or I think better, right? I think the way to do this is M times R times Z hat crossed with R hat. Correct. And then it is better Z cross with R hat is how much? Z cross with R hat is minus phi hat. Right? R hat crossed with Z hat. Help here a little bit. I think so. Okay, I'm struggling here because I'm seeing a mistake. So this is minus phi hat. If you can catch me with that sign, that will help. Okay, that's phi hat. Or is that correct?
I'm
wrong.
seeing M cross R is going into the board.
Yeah.
M cross R is going into the board. Yes, so that's why this is into the board. So this is.
Well, it's.
Oh, so then it is okay. So then it's okay. Good. Okay. Yeah. Why was I seeing it outside? Okay, correct. And phi hat is going into the board, right? Yeah. Okay. Then it's okay. That's fine. But it's still there. Is there something missing?
Well, phi hat, based on, is that in the wrong, is that?
How is M cross R into the board? Oh, yeah, it is. Yeah, it is.
Yeah.
Yeah, it's into the board.
I think I first said it outside, and then I think all of you guys followed me, and then I think I was keeping it confusing. Yeah.
Yeah, it's the right-hand rule for the.
Yeah, but still there is something missing. Okay, we got fixed that. So sign issue is not there, but still I'm not satisfied. I'm saying is this okay? Yeah, this is okay. Like magnitude wise, how about that? Yeah, magnitude wise. Cross product is magnitude of something times
Sine of the angle between them.
sine of the angle, right? These are not perpendicular. So I need the sine of the angle between them. So that's, let's say, theta for a moment. So that's sine theta also, right? Great. And what is r sine theta? That will be this distance here.
Rho.
That's rho, right? That's m rho phi hat. Exactly what is sitting there. All right. So the point is, still have space. A of vector r is equal to mu naught over 4 pi times m, and now this is coordinate independent. I don't need any reference point like z-axis and all that. So this is vector r over r cubed. Very simple expression for the magnetic vector potential. This is just dimensional reasons. If you have a magnet, so think of this as a magnet, north-south direction gives you this. Cross it with the position observation point from the center of the magnet divided by r cubed. So it is 1 over r square actually, because this is a magnitude of. There's a 1 over r square potential, exactly like a Coulomb, but this is potential, remember. This is like a dipole moment, but it comes with a cross. Right? It's a curl picture. It's very simple expression. Once we have this, we can do magnetic field, right? We just have to take the curl of this. Great. Any questions, comments at this point?
Yeah, just
Yes.
something quick. So if we like drop the far field approximation and we include the like other term from the integral, like do we get sort of like quadrupole, multipole terms showing up? Like do those fall out
Yes.
nicely or okay?
Yes, I think that is correct. Let me see, because not quadrupole actually. No, it cannot be quadrupole, right? Is it quadrupole? Because a circular loop has just a magnetic dipole moment. I think it is the smallest element of a of this multipole expansion. So my guess is that it is not that it is having any quadrupole input in there, but it won't. It's not a point. Yeah, this is a point magnetic moment. Like think of a point electric dipole. If you really have a finite, so yeah, the answer to your question is that is if you have a negative charge and a positive charge, right? There is a distribution there. And now if you say this is A is 0, right? So there is 1 point, just a vector in there. That also has a distribution. Right? This size actually leads to some feature in that dipole moment. Still, it is a dipole moment field, but it doesn't, it's not as simple as for a point. Does that make sense? So it is still a dipole, not a quadrupole moment, but the dipole expression is not as neat. It won't be this simple. It's not 1 over R cube. There will be basically there will be A dependence in there. So if you want, if you now release this 1 plus, so that will be a function of A over R. A reasonably complicated, right?
Okay, but that's still a dipole. Okay.
Still a dipole, yeah, still a dipole. Yeah.
Gotcha. Thank
It's
you.
just having some more structure in it. That's a little thing. Yeah. Yeah, still criticize me, but I think that's a correct statement. And pretty much like this, two charges, even if you bring in a distance, it doesn't develop a quadrupole moment in there.
Right.
Yeah, good point. Yeah. And we will get this bigger, like complete expression for this. It won't be 1 plus, or basically, this will come out to be an elliptic integral. So later, 2 weeks down the line, we will do that just because magnet is so important a field that we see around. So it's good to at least go through it. And you will learn a new function, elliptic function. Good to be aware of it. Ever wondered what's the perimeter of an ellipse? Like you have a perimeter, circumference of a circle is 2 pi r. Usually circumferences are very simple. Recall what is perimeter of an ellipse from your geometry.
Is there like a major axis minus?
Yeah, so typically that's what you would think, right? So there is a ellipse is described by this A and B, right? Instead of having 1 radius, it is kind of having 2 radius. So I would think that there is some relation with it, but it doesn't exist. There is no simple formula for perimeter. That's why they don't teach it, right? There is no simple formula for a perimeter of an ellipse. In fact, it is the elliptic integral, right? So similarly, so magnetic field, it is certain things are complicated. So perimeter of an ellipse, yeah. It's yeah, quiz, right? Find the perimeter of an ellipse. Just for fun. Find the perimeter of, or find an expression for the perimeter of an ellipse. It is given in terms of eccentricity. Like it seems like there are 2 parameters here. Instead, what you do is B is written in terms of A, and yeah, a nice expression is eccentricity, which is how much do you squeeze one side. Like more you squeeze, more elongated the ellipse, larger is E. What is the eccentricity of Earth's orbit? Guess. I should say if it's a circle, So circle is E equal to 0, and a straight line E is equal to 1. Okay, so you can really stretch it out. B is 0, that's 1. Guess what's the eccentricity of our Earth's orbit? Is it, how much do you think it is? Yeah, just based on, you have been always told that it is circular, it's pretty good approximation, but then how good an approximation? How much percentage error do you make when you make a circular orbit as an approximation? Like if you were to send a spacecraft to Mars, how far you'll be from Mars if you were to put a circular orbit. So yeah, guess, any guesses?
10 to the minus 3.
10 to the minus 3, 0.001. Anyone else?
10 to the minus 2.
10 to the minus 2, 0.01. Anyone else?
I feel like it's got to be a lot more.
A lot more. Okay.
Yeah, I don't know.
Lot more means 0.5.
Sure.
It's actually 0.01. Moses made it pretty close. I think 0.02 or something. Yeah, that's pretty. The 1% error. If you're designing an experiment which is fine with 1% error, choose circular orbit is way simpler. But if you want to send a mission, you're on a mission where 1% really will decide much more than that, then you have to go for the elliptic orbit. And still, you don't have to worry about Jupiter. How important is it to worry about Jupiter? Jupiter is the most massive object in the solar system. Still, those effects are really small. Jupiter is 1,000 times heavier than Earth, and Sun, but it is 1,000 times smaller than lighter than Sun. And rest everything are negligible. They don't even exist in the 3 significant digits. So a great approximation. That's the 1% error. That's perfect. Fine circle. That's why it's okay. Okay. But we'll come back to this, right? That was all for the motivation to get this point there. Right, we will do that eventually, slowly. But one thing we can probably do, or maybe. So what is magnetic field, right? We did magnetic vector potential, but that was all because we want to prepare ourselves for the magnetic field. But now it's simple, right? Del cross A. And M is a constant, like we're saying direction and the area. And a point dipole moment, by the way, is M is equal to IA square. I think I did say this last time. You're saying that A is small, but then I, in the real point magnetic moment, this goes to infinity. Actually, such that, so this has to go to infinity in such a way that IA square is fixed. In that sense, it has to go to infinity like a infinity square, right? If you want to think of it like that, because it has to cancel that A square, and so it's a growth should be larger than linear. So that's a point magnetic moment we are talking about. Cross of A, there is only 2 terms, right? R and R cubed. Let me quickly do that. So this is we have what is this? Let's see. So this has that's mu naught over 4 pi. There's a simple way of looking at this. Yeah, one thing we can do is actually flip the whole thing, right? For a moment, change it to minus, right? Maybe this will simplify. We can then use our old results. This is del crossed with, so del of A, del crossed with, there is a vector, doesn't really help. No. Okay, so this is equal to mu naught over 4 pi times del crossed with m. Let's treat m as one vector and the other one is as another vector, right? R over R cube. But that's like an electric field, right? An electric field due to a point charge. Whenever you see R over R cube, imagine that to be the electric field or radially coming out. Right? This is constant, so I can now curl. Curl is easy to a curl of a curl, correct? So this is mu naught over 4 pi. And your homework will be to find out what is missing, right? Something will be missing. What is it? Remember, gradient always has to act on everything on the right hand side, but this is a constant, so I don't have to worry about that. So this is m times dotted with r over r cube. And then comes this, so this is minus of mu naught over 4 pi times m dotted with gradient of r over R cube. Okay. And maybe I should just mention this and we'll come back and do this. Like, how much is this? Yeah, just mention that and stuff. What is that? It's one thing I stressed a lot in the last semester. Let's see.
It should be 3 over R cube.
3 over R cube. No. One line quiz on last semester's.
It would be the 4 pi delta to the 3 of R.
Delta function, correct?
Yeah.
Very good, very good. So notice this is like an electric field due to a point charge. Gradient law, the divergence of that is Gauss's law, right? So whatever creates this electric field, that has to come out. But that's created by a point charge. So it's 4 pi delta function. Right? So mu naught, very good. That's m times 4 pi delta cube of r. It's a delta function. The magnetic field has a delta function structure in there. So you want to see all this y, all this is in there. And then there is this piece in there. We can expand this also. Mu naught over 4 pi m dotted with. This has 2 p's, right? So let me do this. I can either act on the numerator. When I act on the numerator, it is gradient of a unit vector. That's a dyadic, right? So that's 1 over R cube. Or I can hit the denominator, which gives me 3 times a vector R remains the same. And if you really do this, so this is R, let's say this is R hat, right? Over R cube. How about this? This is quiz. You have used this many times last semester. What is that equal to? Like, is that a familiar object? Familiar expression from last semester again? This can be written as, I think, can you guys read it online? It's still visible, right? I think so, yeah, I can see. Okay. So this is the same as, except for the delta term. So this is mu naught times m times, you have to go, right? So one more, I won't take more than one. So this is minus mu naught over 4 pi. I'll write this, take this in, m dotted with here. That's m minus 3 times vector r m dotted with r hat over r cube. Where did you see this before? This expression.
That's the multipole.
Dipole. Point dipole had exactly the same expression except that m was p, electric dipole. This was a p, and this was epsilon in the denominator. So magnetic dipole and electric dipole have very similar expressions. Sure, because they look like the magnetic field. But there's this extra term in there. And was it there in electric field also, and we never bothered? And why do we need that? Is it necessary? What does this mean? There's the right magnetic field right at the point, right? It survives only at the position of the dipole. Is it necessary? What's the importance of that? And that is an importance. Electric field, you don't worry about it so much. But here, there is a crucial thing which we will insist on. The point here is that we need this, right? This is a necessary requirement. This is monopole. Otherwise there will be a monopole, correct? So that's why you insist on that. And so that has a meaning. We'll come back and do the last part of it again so that everything seeps in properly. That's all. Thank you.
Could you clarify what the quiz is exactly?
Oh, I actually did. Oh yeah, I did not do it properly. Start from this. So this expression, this box, get the square bracket. Box to square bracket. That's a vector expansion problem. We have used this many times before in the earlier semester. Just, I think, good refresher. Yeah.
So I'm a little confused because how can that be 0? Why doesn't it blow up at that point, just like the electric field?
Yeah. Why doesn't it? Which means that the only way that can cancel is that it shows up again from here there, right? So this is B, remember, right? If I take the divergence there, this will also blow up, right?
Yeah.
And that blowing up will cancel out exactly. And all this feature was there to a certain extent in electric field also. It's just that that didn't bother us too much because, okay, who cares divergence of V? But here, it's slightly more crucial because, or think of it as monopole, right? If this was not 0, even if it is really tiny, you would say that no, go and search inside, really deep inside, which we are not even able to access that distance. There is a monopole hiding there. A theoretician can come and say that, like if it really is not 0. They would say that go and look into the scales that we have not explored. But to our understanding, we have not been able to get that. So that's why you stress on that, it's emphasized. Helps?
Yes.
Yeah. Yeah, simple bar magnet. Oh, yeah, actually, is everyone still there? 4, 5, 6. Yeah. Can I give one more quiz? One more quiz. Yeah. So it's good to, while we are doing this bar magnet. So one more quiz just for this is called. Oh, I should remember this. Yeah. One is Gilbert model of, and the other is called Ampere's model. I think. Yeah, Ampere's model. For a magnet, actually. Like the point is, when we think of a magnet, we know that there is no North Pole and the South Pole. And then you say that, okay, what exactly is creating a field? You say that deep inside somewhere there are loops of currents, right? There are electrons moving around. So the question comes, is there a difference? So Gilbert model is that you really assume that there is a north pole and a south pole. Or at least one of them, I don't remember which one is which. Where one assumes that there is actual north pole existing there, and the other is there is a loops of current there. And the question is, can you think of a situation where they will give you two different things? And to our understanding, both models work the same, but at a fundamental level, you can ask that question. Yeah. So look up Gilbert model. Gilbert is, I think, before. Oh yeah, long back. I don't know which year it is either. Should be long back. I would think 1600, but I'm not sure. Because coulombs is 1700, maybe 1650. Yeah. Not sure. Okay, that's all. Thank you.
Thank you. See you Tuesday.
Okay, bye-bye, John. Aliyah, did you get the quiz? It doesn't matter. If someone doesn't do the quiz, it's, yeah, hopefully Aliyah did get it.
Thank you. See you guys later.
Okay, bye, Michael.
Thank you.
Bye,
Bye,
Aliyah.
guys.
Mhm. Maybe Aliyah will come back. It's okay. Quiz doesn't have to be, all quizzes doesn't have to be great. Bye, Aliyah.
It's okay if we don't do all three.